Hey, so today we move into one of the most important parts of image processing with Python, filters and enhancements. We'll study blurring filters, edge detection, thresholding, morphological operations. These are the mathematical foundations behind computer vision systems like face detection, medical imaging, and object recognition. So, let's start with this. That first, as usually we all know that what image is a discrete 2D signal. So first, here is noise. So what actually noise is? It is the high frequency components in a picture. Suppose you have a picture and where the frequency gets very high, that point is known as noise. And edges. So what is edges? Suppose you have a picture like this, and I have to show you for a little bit. Suppose you have this picture, and what you can see when there is a transition here, the values change rapidly. You can see that these values are literally different than this. So so by using this concept, we can identify the edges. Now, what is blurring? So blurring is basically we need the low pass filtering to suppress the high frequencies. So as we have mentioned before, the noises are very high frequency signals. To suppress this, we will use low pass filtering. So now let's move to what is convolution. Okay, so it is basically slide a kernel over image and multiply the neighborhood pixels with weights and sum them and get a new pixels. So in easy words, think like that. You have a picture like this. Now these are the blocks of the pictures. These are the pixels. Okay, now these have different values. Suppose you pick this size, each have different values. So what we can do, we can average all the values and put same values everywhere, or we can give much more attention or importance to the center value, or there are other ways to do this. So this is how we actually apply the kernel to an image. Now first, if I go about the filtering, we have the average filter. Now before going to this, I would like to explain the mathematical term here, that what actually it is meaning. So the I prime xy, it is the new pixel or new processed pixel that we're getting after applying the convolution or filter. Now here the IXY, which is the original image. So before the change. Now here the k. So what is k? So k is the kernel value at position ij. And what is I and j? It is the offset from the center pixel. Now what k actually is here? The k is how much pixels you are taking for doing the average. It can be 5 by 5 or it can be 3 by 3. So when it is 3 by 3, it means you are taking 3 pixels from the row and 3 from the column like this, and you will average. If it is 5, then you will take more 2 rows here and more 2 columns like this. So this is like a 5 by 5 kernel. So now what we have here, and after all this is the summation, and after all we summation all this and put it in our new pixel. So this is our first filter, which is the average filter. Here we are taking the kernel, which is k equals to 1 by 9. So the mathematical formula should be here is 1 by n square, and then as it is 3 by 3. So when the value is 3, it's becoming 9. And here we have Now maybe there are some different values we will put here after doing average. So every pixels contributes equally with a simple smoothing, and the problem is here the edges get blurred heavily as we are doing it averagely for each pixels without giving any weight. Okay, now let's see in the our terminal how actually average filter look like. Okay, so here is an image. I have already written the code here. So here is the image we have put it, and we can simply just write here blur equals to cv dot blur image, and we're taking here the 5 by 5 kernel. And now if I run this code, you can see this is the average blurred, right? But the problem is, as we have mentioned before, the edges get blurred heavily. And this is the original image, and this is after the average blur. Now let's comment it out because we don't need this anymore. So we can comment it out. Now let's move to our next topic, which is the Gaussian blur, right? Yes. So here we can see that instead of equal weight, what we're doing here, we're giving much more importance to the center pixels. So suppose you have like this part of your picture, and what you want much more give value to this one. Suppose this one is 150, this one is 5, this one is 100, this one is 10, 8, or 300, 300 can't be, the highest value is up to 255. So 250, 200, 1, and 0. So what actually will happen? Before that, we used to average all these values, and then we used to put each the same value everywhere. But now we'll give weight to this value, and each value will be near to this value. So this is what is here we are doing in this calculation. So this is the gxy, which is the weight at position, and here is the sigma, which is the standard deviation, which actually controls the blur strength. And here we use the Euler's number and the exponential, and then we have the xy, which is the distance from the center. Now when pixels are near center, we have the higher weight, and the pixels the far from the center, we use the lower weight. So as we have mentioned, suppose there are a lot of pixels here, and what will happen here, from the center, what is the value of the center? Suppose this value is 15 and others, and so when the values are closer to this will get more importance. Okay, now why Gaussian is actually better? Because in real world, blur follows a normal distribution. Not they actually equally blur everything. Rather, we focus where we have to do much more blur or where we have to do the less blur. Okay. Oh, now let's move to our. Okay, so before that, let's see how actually Gaussian blur looks. So let's move to our terminal and see how actually Gaussian blur works. So I'll comment it out, and let's see the Gaussian blur. And if I run this, You can see this is the Gaussian blur. Now you can simply compare it with the simple blur, which is, where is that? It's an average blur. You can compare these two side by side. This is the average blur and this is the Gaussian blur. So what you can see, in Gaussian blur it's still blurred, but in case of this, everything were blurred used to in same way. And when you see these edges, those were blurred too much, but now the edges are much more visible than before. Okay, now let's move to our next topic, which is median filter. Now, what actually median blur is? So here, instead of averaging, what we do first, we sort the pixel values and then we take the middle value. So it does not blur the edges so much. So let's see what actually is. Suppose you have the neighbor pixels, which is suppose 10, 200, 15, 12, and 14. Then what it will do, the algorithm of it will sort it like this: 14, 15, and 200. So now how it will blur? It will take the median value, which is the 14. So it removes the extreme values. So for noise removal, it's a very great choice. And instead of averaging, we choose the middle value, which removes the noise without blurring the edges. So now let's see in the code how it's actually look like. So let's just comment it out. And if we run, you can see this is what actually median blur looks like. So this is the Gaussian blur and this is the median blur. You can see in case of median blur, it's much more clearer, right? A little bit of animative work if you watch it closely. So what is actually doing, in each kernel it has, suppose this as it is 5, so it's showing that how much it is the intensity of the blur. This is the kernel size. And in case of the Gaussian blur, we also took the kernel size. Okay, now let's move to our next topic, which is bilateral filter. So in case of the bilateral filter, what we have here, that we have this mathematical equation. So what we are actually doing here, we have a spatial closeness and an intensity similarity. What does it mean actually? It's meaning the nearby pixels matter and similar color pixels matter more. So here, this is the mathematical equation. So GS, it is equating the P minus Q, and GR is IP minus IQ. So, and what actually it does smooth regions and preserve the edges. It's a much more advanced technique for doing the filtering. So what it is named as bilateral because we are actually combining two weights here. One is for the spatial closeness and another one is for intensity of color. Now let's see in the code how actually bilateral looks like. Now if we run this, you can see. So this is the bilateral blur. So it's now much more animative if we watch it closely. It's much more animative than the others one. Okay, so this was about all the blur filters what we usually use in our OpenCV and other works. Now let's move to our next topic, which is edge detection. So in case of edge detection, what's the fundamental idea is edges are the rapid change in intensity. So we can find out by using the derivative. So suppose the change when the derivative is so much higher, the change of pixels is, suppose there is a change of pixels, but the derivative will be lower than this. Suddenly the derivative gets higher. So then we can detect here is an age. And this is how actually computer identifies the ages. To do this, we have the formula here, or a Sobel operator, where the dx is the change in horizontal direction. So what does it mean? That if you have an image, suppose like this, and in the x-axis the change of pixel is calculated by this, and for this gy, what does it do? It calculates the change in the y direction. The intensity of the image suddenly increases the value of this. So this is how, using derivative, we can find out the age. And finally, what is that gradient magnitude? It is the gradient magnitude here. And here the large value means the sharp edge and small value means the smooth area. So edges are just places where pixel intensity changes rapidly. So now let's see how does it actually find out in OpenCV using these formulas in our terminal. So first we will remove all this, and for edge detection we can use this, then Sobel X, Sobel Y. This is the code we can actually use for seeing how actually we detect. And if I run this, you can see this is the Sobel Y. So what is actually here it's doing? It is finding out the differences where the intensity suddenly changes higher in the Y direction. And it is for the x-axis where it changes high. So by combining these two, we can actually finding out a clear age. Okay. Now let's see the Laplacian derivative. Okay. So to do this, we have this mathematical formula here, which is del square I by del square I. So it is the Laplacian operator, and we are using here the second derivative, the rate of change of change. So before that, in case of this one, the first Sobel, we use just the change, the where it's supposed from 50 where it becomes 60. Now we are actually calculating that where the change is actually the rate of change of change. Suppose before change was at 5 rate, now where the 5 rate is changing much more, is it going higher or lower? So it is much more, and detects where intensity changes sharply in all directions. So Laplacian looks at how fast the change itself is changing. So it's much more complex and much more advanced for finding out the age. So let's see in the code how it's actually work. So for do this, I'll heal it, and if you run this code, you can see this is what actually Laplacian works, and this detects all the changes where it's changing. Now the most important topic is the Canny edge detector. So it is actually the multi-step math pipeline. So here the algorithm steps are first the Gaussian smoothing that we have already learned. So the Gaussian smoothing, we have an image and we apply here the Gaussian smoothing. Then what we do, we calculate the gradient. that we have already learned before here, how we actually doing the first derivative. Then after that, the non-max suppression. So what it actually do, it keeps only the strongest edges and it remove the thick edges. Okay, and what is the double threshold? Okay, so threshold is doing, suppose you have the like what you can find out that how much it is. So it is if it's strong, if it will be strong if g is higher than your threshold value what you have set, and it will be weak if the value of g is between your threshold values you have set in your code. So what actually it do, there is edge tracking, means it keep the weak edges only if connected to strong edges. So it only keep the weak edges when it is connected to strong edges. Now Canny is not just an algorithm, it's a pipeline of multiple mathematical operations working together. Now let's see how it's actually look like in our code. So what we can do here, we can just write here Canny equals to, and okay, now if I run this, you can see this one is Canny edge detection, and you can see the instead of Laplacian, the Canny edge is much more very good clear result it's giving us for the edge detection. You can clearly see this was the home, this is the bridge, and this is the sky, and this is the sea. So everything is actually detected differently as we have truly applied so much algorithms here. Okay, now let's move to our next topic, which is the thresholding. As we have already mentioned this, so what is the thresholding or threshold logic is? So actually we separate the object from background using a simple decision boundary. So what it is, now we have two thresholds, like weak lower, which is the weak edges, and upper, which is the strong edges. And here in thresholding, we have the I prime, the value can be from 0 to 255, and t is the threshold if it is greater than ixy. So for simple thresholding, we use this code. So here 255 is the max value and 127 is the threshold value. And how actually the simple threshold works, now we move to the code and see how actually it's work here is, you can see if I run this code, here is a simple thresholding. So simple thresholding can be in many ways, right? We have the binary inverse, the truncate, the 2-0 and 2-0 inverse. So these all are the simple threshold, but with some differences. If I run this code, you can see, so this is the binary threshold and this is the 2-0, this is binary inverse. So it's actually the inverse of this one. So where it was white, it becomes black. So it is 2-0 where we detected the zeros, and this is the 2-0 inverse, the inverse of this one, and we have the true and C actually. So this is how we can apply the simple thresholding. Now if I move to our next, which is the adaptive threshold. So what actually adaptive threshold is, that threshold changes per region, and txy, which is mean of the neighborhood, and here what we have, we minimize the intra-class variance. So automatically it finds the best threshold. So the sigma and the weights are automatically detected, and then we use it to find out the best threshold value. So let's see in code how actually the Otsu method works. Now to do this, we just comment out this. So this is the code for Otsu method. So the blur equals to Gaussian blur, then Otsu CV dot threshold blur. This is the Gaussian blur, then 0 to 225, and threshold binary plus CV2 threshold Otsu. So we have applied here the two threshold here, and now if I run this, you can see this is the original image and this is the Otsu threshold. So this is how we can actually convert into black and white, and also find out the difference between the edges, and actually we can change it from the background. I have forgot to show you the adaptive threshold. Sorry for that. Let's move a little bit backward. I forgot to show you it in our code. So here we can see the adaptive Gaussian and adaptive mean. So this is the adaptive Gaussian and this is the adaptive mean. We have used, first we did the Gaussian blur, then use this adaptive threshold, and this the after the Gaussian the mean blur, we use the adaptive mean. So this was the topic we just missed. And okay, now let's move to our next topic, which is the morphology. So what's actually the morphology is, it's actually using a structuring element to modify shapes. So here we have the erosion. So it actually shrinks the objects, and here is the code for that. And we have the dilation, so which actually expands the regions, and we have opening, which actually removes the noises, and we have the closing, which actually fills the gaps. And these are the morphology on OpenCV. Now if we see it in the code, what we have here, just the displaying the all the dilation operation here, and we'll just comment out before the this one, we'll comment it out, and we can see only the morphological part. So in this code, you can see here the kernel structure. We take the 5x5 kernel, then in erosion CV2 erode the threshold binary, then the kernel, then the iterations of 1. Then for dilation CV2 dot dilate threshold binary kernel iterations 1. And this is how we can apply all this, and we can just, so we have the all the opening on erosion and black hat, top hat, we didn't discuss that, but the gradient, the closing, the dilation. So every kind of detection, the morphological operations, what you can apply here. So in further much more advanced video, we'll know about this more. And for today, this is enough, I think. And thank you for being with us.